Differentiation is looking at the change in a function. We already know what the average rate of change is. And that's given by our change in our function value, so f of b minus the f of a, and we divide that by our inputs, a minus b. The average rate of change only really works when b does not equal a. So that means that we cannot find the rate of change at an individual point. What does this really mean? Well, let's look at a graph. Looking at this graph, if we just chose two random points, our point here and our point here, we could indeed find the average rate of change between them. However, what happens if we just didn't want to include this point? We only wanted to find the rate of change at this point. Well, the average rate of change only applies when we have two different values. So we can't do anything about this. Or can we? Well, seeing that this equation has a straight line, we can pick any one of these points along, and we can really calculate what the average rate of change is, even though we have only been given the single point. But what happens if we have this sort of function? With this one, we can't really see any real point along the line that kind of matches up between our inputs and our outputs. Well, maybe apart from that one here, but even at 1 down here, the value does not exactly sit on the line. So how can we find the rate of change between here or here and our point down here when we can't find what the value is at this point because it just does not line up properly? We could make an estimation, but it's not going to give us our value. What we can do is look at how the function changes as we get closer and closer to this point. So taking our average and making each of those averages smaller and smaller and smaller until we reach our actual point. But our current definition for an average rate of change is not really going to give us this answer. But this is where derivatives are going to help. So our derivative is going to look at a tiny point on our graph and see that its rate of change at that point, and we can choose that for any point along, and it should give us a derivative and a function value at that point. So how are we going to find the rate of change at a single point when we've got a value here that only deals with 2 points? Well, first of all, let's clean this up, and we'll just put that point back in. Now, let's just call this point here that we're looking at as a value of f of x. Now, to use our average rate of change, we need to have another value in here. And that's going to be another value that's going to show us somewhere along here that it's going to be the rate of change of it. So let's just add another point here. And if this is x, I'm going to call this x plus h. So now we can put in our value here of x plus h. So now just filling off our average rate of change, we'll just add the minus in and our 2 different points. So our x plus h and our minus x. Now we can simplify this. The top doesn't change, so f of x plus h minus f of x, but our bottom can change. So looking at this part down here, we have a minus x and a plus x. Those cancel, and we're just left with an h down the bottom. But this is still looking at 2 points further apart. What we need to do is look at when h pretty much doesn't exist, and we're going all the way back down to our original point. So what we do is we take our limit as h tends towards 0 of our derivative function. So our f of x plus h minus our function at our point over h. And this is called taking the derivative at first principles.